In this video, I'm going to simplify and explain how large language models like Llama 270B and ChatGPT-4 are trained. We will go through the details of how large amounts of data are compressed to train the models and the hardware and costs associated with it. We will also break down and explain the methods of how neural networks in large language models like ChatGPT predicts the next word in a sentence. This is the second video of the video series I'm creating on large language models and how they work. This video series is designed to simplify these complex topics as much as possible, so whether you have a technical background or not, you will find this helpful. This video is based on the following resources. First, Dr. Ande Karpathy from OpenAI. He has given several lectures on how large language models work. Second is going to be a published paper called Attention is All You Need. This was published in 2017. You can find this paper on archive.org. And then lastly, Llama 2's technical documentation, which can be found at llama.meta.com. I've posted the links to the resources below in the video description for your reference. Training a model like Llama 270B is far more complicated than simply using it. This process, known as model training, involves crunching a massive amount of internet data known as data compression. So what does this mean? Compressing internet data to train a large language model refers to the process of taking vast amounts of text data from the internet and condensing them into a format that the model can learn from. This is necessary because the internet contains enormous amounts of information, far too much to be processed by any model in its raw form. So this is achieved by simple steps. First of all, collection of data. So large amounts of text data is collected from the internet. Again, this could include websites, articles, books, and forums, which is then pre-processed. And this step can involve removing unnecessary parts like HTML code, correcting errors, and simplifying the complex structure. Next, the text is broken down into manageable pieces such as words and subwords, which are known as tokens. The tokens are then converted into numerical values or vectors that the large language model and the neural networks can understand. So the model then learns from this processed data by adjusting its internal parameters, which are known as weights. So by doing this, the model is not necessarily memorizing the text, but learning patterns, relationship, and information contained within it. For example, from reading numerous articles about weather patterns, the model learns the relationship between temperature, humidity, and the likelihood of rain without storing all the specific details of each article. Let's consider another example of data compression. Imagine the internet has a million articles on climate change. Directly learning from all these articles would be impractical. Instead, through training, the model compresses the knowledge contained in these articles into a set of parameters. Later, when asked about climate change, the model uses these parameters to generate responses that reflect the understanding that's gained from those articles without having to refer back to its original text. This process allows the model to quote-unquote compress a broad and complex data set into distilled form, enabling it to generate text, answer questions, or perform other language-based tasks with the understanding of the topic that it has been trained upon. Alright, so let's take a look at how this data is compressed. To compress large amounts of data gathered from the internet, you need large clusters of special computer known as GPUs. GPU stands for Graphics Processing Unit, which is a specialized processor originally designed to accelerate graphics rendering. For those of you who are gamers or have built your own PC at one point, you know exactly what I'm talking about here. Simply put, GPUs can process many pieces of data simultaneously, making them useful for machine learning, video editing, and game application. GPUs for AI are the reason why NVIDIA has become one of the largest and most profitable companies in the world today. If you go to NVIDIA's website, you can see that one of their products is the GPUs. Under products, you can see that the GPUs, they have several types of GPUs, but the ones that are used specifically for AI are the data center GPUs. Again, we'll go into the details in a little bit of how Llama 270B actually uses NVIDIA's A100 GPU to train their model. So the process of compressing this data is extremely expensive and requires a lot of energy. Since Llama 270B is open source, Meta has actually shared these details on its training, revealing that it involves analyzing around 10 terabytes of text from various websites. So let's take a look at Llama 270B's numbers. So the collection of data, so they have collected 10 terabytes of text data. The hardware that they used was NVIDIA's A100 GPU, and it took them 1.72 million GPU hours, which is approximately 12 days, to compress that 10 terabytes of data, the text data, into a 140 gigabyte file. So you could see that compression has a huge impact on that data from 10 terabytes to 140 gigabyte file. And it costs them roughly about $2 million. So let's take a look at these numbers and confirm them. So if you come to llama.meta.com and click on Llama 2, you can actually come down here, click on the technical specification, on read the paper, and then it will bring you to the paper here, and you click on download, and this will take you directly to the paper here. Let's zoom in a little bit. I'm going to scroll down to page 6, which is the pre-training. And then right here, as you can see, so the Llama 270B model, it's a time GPU hours, and the 70B model, as you can see, it's 1.72 million GPU hours. And it talks about the power consumption and the carbon emitted, but that's, we don't have to focus on that. So let's go ahead and quickly calculate this. All right, so let's pull up this calculator. So if we put so that's 1.72 million GPU hours. And if we divide that by 24, so there's 24 hours in one day, we get 71,680 days. But now let's divide that by 6,000, because again, they use 6,000 GPUs simultaneously. So if we divide that by 6,000, we get 11.95 days, which again, approximately 12 days. And then also as far as the hardware they use, so if you take a look at here, training hardware carbon footprint, let me zoom in a little bit more. So they said both clusters use NVIDIA's A100 GPU. And again, if you go to NVIDIA's page, this is NVIDIA's 100 tensor core GPU. I don't know if they use the tensor core GPU, but essentially this is pretty much the same. And you can read the explanation and the white paper on what this GPU does, but essentially it's for enterprise ready software for artificial intelligence. So NVIDIA has designed this GPU specifically for artificial intelligence and amongst other GPUs as well. But since Meta has explicitly mentioned this NVIDIA A100, so we can safely say that this is exactly the GPU that they used. Whether it's the Tensor Core GPU or not, that's to be determined. So knowing the numbers from Llama 270B, we can actually guesstimate ChatGPT-4's cost and the consumption or the amount of money it cost them to train their model. So I've put together a few estimates. Again, these are just estimates that I have done. They're not accurate. They might not be accurate, but at least we can take a guess based on the parameter values that we know both for ChatGPT-4 and then also for Llama 270B. So Llama 270B, as I explained in my previous video, so feel free to check that out so you understand what parameters are if you haven't already. But Llama 270B, they have told us in their website that has 70 billion parameters, and then we also know that ChatGPT-4 was trained on 1.76 trillion parameters. So if we divide 1.76 trillion by 70 billion, we get about 25x, which means that there's 25 times more parameters in ChatGPT that it was trained upon versus Llama 270Bs. So based on that, we can actually estimate the rest of the numbers as well. So for hardware, so let's assume that they use 6,000 GPUs as well. If it took Llama 270B 12 days, if we multiply that by 25, it would take 300 days for ChatGPT-4 to be trained, assuming that they use 6,000 GPUs. Same thing with the cost, because Llama 270B, it costs them around $2 million. If we multiply that by 25, it will give us $50 million, meaning that ChatGPT-4 costs $50 million to train the data. Again, these are just numbers that I estimated based on the parameter differences that are between ChatGPT-4 and Llama 270B. All right, so now that we understand how large language models are trained, let's take a look at how a large language model or the neural network, which is the engine behind them, actually work and what they do with this available compressed data. So large language models like ChatGPT are based on the foundation principle introduced in the research paper that was named Attention is All You Need, which was published in 2007, and you can find this in archive.org. This is the paper, so all of these people from Google Brain, University of Toronto, and then a few other individuals. So you can go ahead and read through this documentation if you want to know exactly how the transformer model works. But to summarize it, simply put, in large language models, neural networks are the main engine or the system behind them. So they have the ability to predict what words come next in a sentence. So they learn this skill by reading through enormous libraries of text that it has been trained upon, picking up on how words and phrases naturally fit together. So imagine a computer reading countless books, articles, and websites, then starting to recognize the patterns, like how, for example, cat sat on a often ends with words like mat or rug. So what the neural network does is when it reads cat sat on A with a 97% probability, it can estimate that the next word is going to be mat. And over time, it gets better at guessing the next word by remembering what usually comes next in a similar sentence. And just to clarify, this isn't just about memorizing words. So large language models are not memorizing words. It's about understanding the flow and the rules of a language, even grasping different writing styles. So the more it learns, the better it gets at making educated guesses, leading to writing that can be surprisingly human-like. I always like to give example of how our incredible brain works similar to this as well. So an example of how our brain's neural networks work similarly to predictive models in large language models or in language processing is our ability to understand jumbled words in a sentence. As long as the first and the last letters of each word are in a correct place, this phenomenon is often cited to demonstrate our brain's pattern recognition capabilities. So for example, consider this sentence. Despite the internal letters being scrambled, most people can read this sentence without much difficulty. So it's read, I can't believe how easy it is to read this sentence. This ability comes from our brain's neural networks, which have learned language patterns and can predict words and their meanings based on context and position of certain letters. Our brains do not read every letter by itself, but rather recognize the overall shape and structure of the words. This pattern recognition allows us to quickly process and understand written language, even when it's not perfectly presented, showcasing the brain's remarkable flexibility and adaptability, akin to how neural networks in machine learning can predict and interpret information based on learned patterns from data. So when that 10 terabytes of text gets compressed to 140 gigabyte file, for example, in Llama 270B's model, it's not necessarily absorbing all of that data per se or referring to it, but from that text, it learns the patterns and then it interprets, and based on that, it predicts the next word on a sentence and has the ability to, like I said before, write like human beings. All right, so that's how large language models are trained and the hardware that's used. So in this video and the previous video, they were the first step in training our system, which we call pre-training, where we lay the groundwork. Next, we move on to the process called fine-tuning. This is where we refine our system to become what we call an assistant model. So the aim is not to just create something that can write text. That's quite basic, right? Instead, we want to build a system that can understand questions and provide relevant answers, making it more useful for a variety of tasks like what ChatGPT does today. So in the next video, we'll go through how large language models are fine-tuned to make them incredibly useful for a variety of topics. Hope you found this helpful. Thanks for watching and stay tuned for the next video.